Lecture, I apologize. Welcome to Math 150, Section 2, Lecture 15. So what we're going to do today is we're going to prove the fundamental theorem of calculus. There are not that many fundamental theorems in mathematics. You do not get the name lightly. Right? So if you have the name fundamental, this means it is something you should know. You have hopefully seen two other fundamental theorems by now. You might have seen the fundamental theorem of arithmetic. I can write any number as a product of prime powers, and I can do it uniquely if I list the primes in increasing order. Or you might have seen the fundamental theorem of algebra. If I give you a polynomial of degree n, it has exactly n roots. Some of the roots may occur multiple times, but there will be exactly n roots. When you get to linear algebra, you might meet the fundamental theorem of linear algebra. I actually think that one's a little bit overrated. I don't think it quite merits the title of fundamental. It's one of the reasons I don't teach linear algebra here. You might take probability, and you will have the central limit theorem. So they don't use the word fundamental, but central, I think, is close enough in terms of spirit that this is almost the same as a fundamental theorem. I am not going to give the most rigorous proof possible. I'm not going to prove things in the most general case possible. I am going to assume additional properties about my functions so that I can simplify the proofs. So typically when you do arguments, why do you have assumptions? It's either wrong if you don't have the assumption, or it makes the proof a lot easier. What class do you think you should take if you want to get rid of some of these assumptions? Real analysis. Okay? And so what I want to do is I want to start today with the intermediate value theorem and then do one of its consequences, the mean value theorem. How many of you have ever watched the TV show Friends? Except for at most 2 episodes, what does every title of a Friends episode begin with? The one with. So today's lecture is the one with the mean value theorem. When in doubt, if I ask you a question of what theorem should we use, you have a really good chance to say, oh, mean value. You want the tone right too. Okay? You may be wrong, but odds are very good if I ask what theorem should you use, it's the mean value theorem. I want to really build the lecture and show just how powerful of a result that is. All right. So let's start off with the intermediate value theorem. So intermediate value theorem. If f is continuous on AB and C is between f of A and f of B, then there exists a C in the interval AB such that f of little c equals big C. So another way of viewing this is all intermediate values are assumed. I'm going to try to switch which lights are on. No, it's even listed. So all intermediate values are taken on by the function. It is essential that the function is continuous. Otherwise, have it equal f of A for the first half of the interval, f of B for the second half, and you have this jump discontinuity. Yes? This one?
Yeah.
That means there exists.
The C with the two letters.
Oh, I'm trying to do capital C. So I'm trying to do this as a capital C, and then there's a lowercase c associated to the capital C. So it's actually interesting. In a lot of math books, they use bold for various symbols. But because bold doesn't show up well on the blackboard, they then do things such as, it's called Math Blackboard R, or Math Blackboard C, or Math Blackboard Q. And now people start using these in textbooks as well, and I admit I do this as well. And there's no need to use these in textbooks because you can actually just use the bold. And so I actually have a colleague who is writing a contribution for a book I'm editing where he's very adamant that for his section, do not use any of these symbols or I will be upset with you, Steve, because these symbols should not be used in a math book. They're only being used because you can't do bold. If you can do bold, use bold. So I'm trying to have the notation good. Little c goes to big C. So I'm going to try to do enough of a proof. So here's A, here's B, maybe here is f of B, maybe down here is f of A. And then we're saying if there's any intermediate value C, there will be some point in between where f of little c equals big C. Does this remind you of anything we've seen this semester? And let me add a point. Let's look at the midpoint, a plus b over 2. If that equals big C, we're done. If it's greater than big C, then let's look between a and a plus b over 2. If it's less than big C, let's look at a plus b over 2 to b. Does this remind you of anything you've seen before? Which method?
Newton's.
Not Newton's method. The method that Newton's method destroys. Divide and conquer. This is basically divide and conquer. So we'll have a sequence of points. And we'll have a0, b0, which is the initial interval ab. Then we'll have the interval a1, b1. And let's say over here, in this case, it's smaller. So in that case, it would be a plus b over 2b. And we would have a2, b2. And so on and so on and so on. And so if we do this, we end up getting a sequence of points. So we have our left intervals, a0 less than equal to a1, less than equal to a2, less than equal to. And that's going to be less than equal to b2, less than equal to b1, less than equal to b0. So it's always a question of how much rigor do you want. Each time I'm having my interval. The a's, the left endpoints, are only traveling to the right. The right endpoints are only traveling to the left. And because they're getting closer and closer and closer, they have to converge to a common value. So the a's are converging, and the b's are converging. What should we call the point that the a's converge to? Sorry? I can't hear you. Well, we don't know. It's not necessarily the midpoint. They're converging somewhere. What should we call that point? Not A, because A is the left endpoint. Yes. We should call it C. There is some point C. This is going to be how we get our candidate. And because of continuity, we know that at all these left endpoints, f of the left endpoint is no more than big C. And we know f of the right endpoint is going to be greater than or equal to big C. So when we look at the functions f of an, and we look at the functions f of bn, because an and bn converge to a common value, this has to just be evaluated and give us the big C. Okay? So because my function is continuous, and the a sequence and the b sequence converge to a common value, the f of the a's and the f of the b's must converge to a common value. What's the only thing that could happen for that common value? Well, we know f of all the a's is at most big C. We know f of the big b's is at least big C. So the only thing that's possible in the limit is that it actually equals big C. And this is the intermediate value theorem. Okay? This is one of the big results from calculus. One of the things we're going to use it for right now is the mean value theorem. So let's say f and f prime are continuous on AB, then there exists a little c in the interval AB such that f of b minus f of a over b minus a is f prime of c, or another way of writing this is f of b minus f of a is f prime of c times b minus a, or yet another way of writing this is f of b is f of a plus f prime of c times b minus a. All three of these expressions are useful. And what's going on is, here's A, here's B. I'll move B a little bit further down. Look at the x-axis as time. Look at the y-axis as distance. So if I plot distance versus time, the slope of the distance versus time graph is going to be my speed. So if I look at the slope of the line from here to here, that's going to be my average speed. And what the mean value theorem says is there's at least one point, and in fact in this case there's two, where your instantaneous speed is your average speed. Right? I'm going to give you the proof by no shit. Okay, it's a nice method of mathematics. Right? Imagine your average speed is 50 miles per hour. Could you always be traveling less than 50 miles per hour? Why not? Yes? Well, we haven't proven the theorem yet. Yeah, if your average speed is 50 miles per hour and you're always traveling less than 50 miles per hour, how the hell did your average get up to 50? Similarly, if you're always traveling above 50 miles per hour, could your average be 50? No. So you must have traveled at 50 miles per hour at least one moment in time. We can write this more rigorously, and we can make this look more like a math theorem and math proof. If there's time at the end of the class, I'll do that. But really intuitively, that's what's going on. It's the intermediate value thing. All right. Why am I writing it 3 different ways? These different expressions are useful for different things. So over here, this is telling me my average speed is my instantaneous speed at one point. Over here, this is telling me the distance traveled is my speed at a proper moment in time times the elapsed time. And the last one is where I am at B is where I was at A plus some special speed times the elapsed time. So later in the semester, when we get to Taylor series, we're going to try to expand where we are from where we started. And we'll want to replace this, not evaluating this at C, but evaluating this at A, at the starting point. And it will no longer be an equality, it'll be an almost equality. Now, in the mean value theorem and the intermediate value theorem, they're nice theorems, but they don't give you all the information you might want. What piece of information would you like to have that they don't give you? Any thoughts? Yes? Where they are. There is some point. Where's that point? Where's that point? They don't tell you where the point is. They just tell you the point exists. Now, amazingly, for a lot of things in mathematics, it's enough to know that there is such a point. And once you have that point, you can actually deduce wonderful consequences from it. So how many of you have seen a proof of the fundamental theorem of calculus? Okay, not everyone. How many of you remember and understand the proof of the fundamental theorem of calculus? All right, much less. Okay. So we will do a proof of the fundamental theorem of calculus, which will lead into what's going on in several variables. It's really worth spending the time and reviewing this and seeing what's going on. And it turns out that what we're doing, it's absolutely fine that these are non-constructive proofs. It is fine that it's just an existence statement. We do not need to know where those points are. If you wanted to know how quickly are we converging to the true area, then it would matter. But if all you want to know is what happens in the limit, we're fine. One of the advantages of having you watch things in advance and prepare for class is this frees up time to do some other things. So what I want to do now is I want to give you an example of a non-constructive proof which you might find unsatisfying. If you like this, one of my thesis students is doing a thesis on a game involving the Fibonacci numbers that I created. And she's able to prove that the game begins with an input of an integer and then 2 people go back and forth. As long as you don't choose the number 2, player 2 always has a winning strategy. We have no idea what that winning strategy is. It is a complete existence proof. And so what I want to do is I'll show you a simpler game where I can prove to you that player 1 can always win. But I have no idea what player 1 should do to ensure that they win. I just can prove to you that they will always win if they play correctly. And this gives you an example of how unsatisfying these general existence proofs can be. You want to know more than just it can be done. You want to know how should I do it. Would you rather go first or second in this game? First. I told you player 1 has a winning strategy. All right. If I had to choose, I'll go first just because I know maybe I'll be lucky. So it's a game of dots. And the way it works is on your turn, you choose a dot, and you eat all the dots above and to the right of that dot. And whoever goes last loses. And when there's no more dots, the game is over. Where would be the worst possible place to go on your first move?
You said above and to the right.
So if I go here, I would eat all the dots above and to the right. I would eat these 8 dots if I go here. Where's the worst place for me to go? Bottom left. If I go here, I automatically lose. Stupid move. I will prove to you player 1 has a winning strategy. I'm going to break this into cases. Case 1, player 1 has a winning strategy. Play it. Okay, I'm comfortable with case 1. If player 1 has a winning strategy, play your winning strategy. What's case 2? I'm sorry? So what does it mean for player 1 to have a losing strategy? If player 1 doesn't have a winning strategy, who has the winning strategy? Player 2. So imagine player 2 has the winning strategy. On player 1's turn, their first turn, they choose to go there and they eat that one dot. It's player 2's turn now. They have a winning strategy. What should player 2 do? I'm sorry?
E1 dot.
Which dot?
The one on the left.
Why that one? Player 2 has a winning strategy. What should player 2 do at this moment in time? I'm sorry? Play their winning strategy. Do I know what their winning strategy is? Hell no. Let's say their winning strategy is to choose this point and eliminate all of these. So what that means is when the board looks like this and whoever has just gone, they're the ones who win. Let's turn back time now. Where should player 1 have gone on their first turn? Where player 2 goes to win on their second turn. Because notice, if player 1 goes here, they just eat this one dot. When player 2 goes here, they eat all these dots. If player 1 just goes right here, it's as if player 1 and player 2 have switched roles, and now player 2 is going first, and now player 1 is going second. So if player 1 goes there on their first turn, they would win. So this proves that player 1 has a winning strategy. And I can't tell you what it is. So if you were to play me, you have a good chance of beating me. I don't know what it is. So it can be very frustrating at times to have these general existence proofs. Sometimes, however, that's all we can do. We can't do better than just it exists. All right. So we need a few other preliminaries before we prove the fundamental theorem of calculus. I'm going to assume certain functions are bounded. Right? If you take which class, can we drop this assumption? Real analysis. Right? I'm not asking for a theorem. If I was asking for a theorem, you would say mean value theorem. Right? If it's a class today, it's probably real analysis. So we say f is bounded on AB if for all x in the interval AB, we have f of x in absolute value is at most b for some b. So there's some number such that no matter what input I take in my interval, the value of my function in absolute value is no more than b. You have seen boundedness all the time. Frequently, we don't need the best bound. We just need a bound. Sometimes if you don't have the best bound, you may not have the best possible consequences, but it's good enough for a lot of purposes. Has anybody ever written in this device called an elevator? Really cool. Okay, excellent. How would elevators be related to boundedness? Where's the boundedness in an elevator? You can only go up and down. So interestingly, this was also the first example in the 9 a.m. section, that when you look at the elevator, you can only go to a certain height, and you can only go down to a certain height. There's another way, another application of boundedness in elevators. Yes? Oh, well, that's related to the first one. That they have to go in a certain range. So, well, that's related to how much it holds. You know, don't you guys read the inspection stickers and the weight capacities and just worry about who's in that elevator with you, right? This elevator can take at most 1,000 pounds. Do you think it's exactly 1,000 pounds? Do you think 1,001 pounds would destroy the elevator? Why do you think they go a little bit below? Any thoughts as to why they go a little bit below?
They don't expect people to know exactly their weights and
All right, so people may not know exactly their weight. You know, you probably don't have a little. Okay, I'm a little bit worried before we get in. Could everybody please tell me their weight to 2 decimals? To be cautious. Yeah. The consequences of missing by a little bit is disastrous. Same thing for bridges. They deliberately underestimate. A lot of military applications, a lot of airplanes and whatnot, you deliberately underestimate so you have some safety margin. So we've seen boundedness many times. So for example, let's say I give you the function f of x equals 3e to the 4x plus cosine x to the 8 sine of x minus 11x cubed, and we'll say 0 less equal to x less equal to 1. Let's show that this function is bounded. I don't care about what's the smallest bound. I just want to show it's bounded. So the absolute value of a sum is less than equal to the sum of the absolute values. Because x is between 0 and 1, what's the largest 3e to the 4x could be? Yes. 3e to the 4. What's the largest cosine x to the 8 sine of x could be? So I think you got it. It's at most 1. Are you overestimating or underestimating? Could it ever exactly equal 1? So sine and cosine are individually between minus 1 and 1. If cosine of x is 1, sine of x is 0. Similarly, if sine of x is 1, cosine of x is 0. Cosine x to the 8 sine of x is never going to be exactly equal to 1. You have overestimated, which is absolutely fine. How would I find the largest value this could take if I really cared? Yes? Excellent. So I'm so glad you said check endpoints as well. So we can just take the derivative, find critical points, check endpoints. But if we just need that it's bounded, it's not worth doing this. What about the minus 11x cubed term? What's the largest contribution that that would give us? I'm sorry? Plus 11. We could say, well, this is always negative, but then we have to be a little bit careful because, well, what if this quantity here were negative as well? Maybe the negative 11 could override that. So let's just say it's at most plus 11. All right, does everybody agree e to the 4th is at most 10 to the 4th? So this is less than equal to 1 million. Yes?
Sorry, how do you get plus 11?
I have to take absolute values.
Yeah.
So I want the absolute value of f of x to be at most b. What if I give you, say, f of x equals negative 11x cubed? You don't want to say f of x is less than equal to 0 for x in 0, 1. Because if I take x equals 1, I get negative 11. I have to make sure I put in absolute value signs. So if I have f of x equals a of x plus b of x, or even minus b of x, then I would say the absolute value of f is less than equal to the absolute value of a of x plus the absolute value of b of x. So when now this is being wasteful. The fact that I have a negative 11x cubed here and a positive 3e to the 4x, these are going to be canceling each other. My bound sucks. But I just need a bound. I just need to show that there is some b that works. And what we're going to do later today, the actual value of b does not matter. So if you wanted to find the best value, then you could take endpoints, you could take derivatives and find critical points. We're not going to bother doing that. Okay, so this is all I need about this notion of boundedness. All of the functions we're going to be looking at, it will not be hard to show that they're bounded. We're going to be looking at nice functions on finite intervals. It all follows. If you take real analysis, it turns out that if your function is continuous on a bounded interval, it's automatically bounded. So you don't need to assume boundedness. You actually get boundedness by doing some more work. All right. So it's now time to state the fundamental theorem of calculus. So assume f and f prime are continuous and bounded. Let the integral from a to b of f of x dx be the area under y equals f of x from x equals a to x equals b, let big F prime be equal to little f. So big F is any antiderivative of little f. Then the area under the curve from a to b of f of x is big F of b minus big F of a. So it's very important to remember what the fundamental theorem of calculus is stating. If you do not include the word area, you're basically just doing the fundamental definition of calculus. The reason this is useful is that this symbol here represents area. And this tells us how we can compute that area. Okay. This symbol does not mean evaluate big F at b and subtract big F of a. If so, there's no theorem. That's just a definition. The theorem is that this represents area. And we have to be careful. Area can be a signed quantity. If we have something like this would be positive area because it's above the x-axis. That would be negative area because it's below the x-axis. Other things that are worth mentioning is big F is any antiderivative of little f. If I have two antiderivatives that have the same derivative, must they be the same? Or could two different functions have the same derivative? So they could differ by a fixed constant c. So imagine I change big F by 5, then I would add 5 to this, but I would subtract 5 from this and it would cancel out. That's why it doesn't matter which antiderivative I take, I can take any. Remember when we dropped the chalk? All that matters is the change in potential energy. The change in potential became the change in kinetic. I can choose where ground zero is. It can be the floor, the ceiling, whatever. It's the change that matters. Okay. Any questions about the statement? Got a little bit under 25 minutes to prove the fundamental theorem of calculus. All right. So proof. So without loss of generality, let's assume a equals 0 and b equals 1. I don't need to do this, but it's just going to make the notation a little bit easier. So here's 0, here's 1, here's 1 over n, 2 over n, k over n, k plus 1 over n, etc., etc. And I'll call this point xk, and I'll call this point xk plus 1. So I'm chopping up my interval 0, 1 into n parts, each of size 1 over n. And let's blow up, here's xk, here's xk plus 1, and here is a plot of my function in this interval. I'm going to choose a couple of special points. I'm going to call this point Lk. This is where my function is smallest on the interval. I'm going to choose another point over here, Uk. This is where my function is largest on the interval. So you need to prove that such points exist, that there is a point where the function is largest, there is a point where the function is smallest. It's very important that I have a closed interval that I include the endpoints. What class would you prove this in? Real analysis, right? When in doubt today, the class is real analysis, the theorem is mean value theorem. In real analysis, you will prove if you have a continuous function on a closed bounded interval where you include the endpoints, there's always a point where it's largest, there's always a point where it's smallest. Quick sketch is basically divide and conquer again. Imagine you have a sequence of points where the function is always getting larger. So I look at that sequence of points, then that sequence is going to have a subsequence that converges, and by continuity, it's going to have to then take on that value. If people are interested later in the semester, we can prove some of these things rigorously. We're going to have time so that we can get to some of these topics if you're interested. If you're not interested, I see no point in making you, listen to it. But if you want to, let me know. So if I try to look at what's going on here, if I assume my function always takes on the value f of Lk, there will be a lower bound for the area in this part. And if I assume it always takes in the value f uk, that will be an upper bound. So the true area lives somewhere between these two rectangles. And so what I get is f of lk. Now what's the length of this interval? So how far is it from xk to xk plus 1? Sorry?
1.
Nope, the whole interval is 1, going from 0 to 1. How far is it from xk to xk plus 1? You're close. I'm sorry? It is x1, but there's a better way to say x1 than that. It's 1 over n. This point is k over n. This point is k plus 1 over n. So the difference is just 1 over n. I'm chopping up the interval into n equal subintervals of size 1 over n. So if I take the smallest value times the length, that'll be less equal to the area of the kth piece. And that will be less equal to f of uk, the largest value, times 1 over n. So the true area in the kth piece is sandwiched between these. So if I add them all up, so I sum k goes from 0 to n minus 1. When k is 0, we go from 0 to 1 over n. When k is n minus 1, I go from n minus 1 over n to 1. So I have f of lk 1 over n is less equal to the area, is less than equal to the sum k from 0 to n minus 1 of f of uk times 1 over n. So we'll call this the lower sum. We'll call this the upper sum. And then the true area lives somewhere between the lower sum and the upper sum. Now, one of the things that can be a little bit annoying is as n gets larger and larger and larger, what would you like the lower sum to converge to? As you take more and more points, what should the lower sum converge to? For this to work, what does the lower sum have to be getting closer and closer to? The area. And what does the upper sum have to get closer and closer to? The area. It's possible that the lower sum is getting closer and closer and closer, then gets a little bit worse, and then gets closer and closer and closer again. The problem is if I go from n points to n plus 1 points, I change all of my intervals. And it's possible that the lower sum could actually get a little bit worse before it gets better again. One way to avoid this is you always do what's called a refinement. I first start off with the interval 0, 1. Then I choose the midpoint and I have 0 to a half to 1. Then I choose the midpoint of those two and I add the 1/4, then the 1/8, then the 1/16, then the 1/32. And if I do it like that, I will always get better. Or if I don't get better, I'll at least stay the same. I'll never get worse. So in that case, the lower sums always converge upwards, or at least staying the same. So the lower sums never get worse, the upper sums never get worse. We're not going to do that. We'll consider the general case, but I just wanted to alert you. So the hope is that un minus ln converges to 0. Because if that's true, well, the area lives between the upper sums and the lower sums. So if they converge, if the difference between them converges to 0, then each of these must be converging to the true area. Right? So it turns out that this is true. So we will now prove that the upper sum converges to the lower sum. So proof un minus ln goes to 0. So we know that the lower sum can't be larger than the upper sum. I'm going to just try to move this so that the glare and light is not as bad. So we know that the lower sum can't be worse than the upper sum. And we know that the upper sum can't be smaller than the lower sum. How far apart could they be? Well, let's look. So un minus ln is going to be the sum, k goes from 0 to n minus 1, of fuk minus flk times 1 over n. So when you see that sum, what's the first thing you should do to try to understand that sum? What should we do to that sum? what sense?
1 over n, and then the sum.
So you want to multiply each term by 1 over n? I wouldn't do that.
Say that for last and distribute the sum.
So what do you mean by distribute the sum? What should we do to this 1 over n?
Take it out.
Take it out. Pull it outside. So this is just going to be 1 over n, the sum k goes from 0 to n minus 1 of f of uk minus f of lk. And now this is giving us some hope that maybe this sum is small. We're multiplying this sum by 1 over n. N is going to infinity. So that should make things really, really small. The problem is 1 over n is going to 0, which is great. But how many terms do we have in our sum? We have n. Oh god. The number of terms we have is going to infinity. If each term is of size 1 over 100, I have n of them. And that n will cancel out the 1 over n. So for example, here's a very, very bad function. Let's let f of x be 1 if x is a rational number, and 0 if x is not a rational number. This is a horrible function. It is wildly discontinuous. Now we're assuming our function is continuous, so we can't look at this function. But let's say we tried. In every interval, there's always going to be a rational number, so the upper sum is always going to be, what's the upper value always going to be? 1. And in every interval, there's always an irrational number, so what's the lower sum going to be? 0. So we would always get a 1 minus 0, so we'd always get a 1, and we would get the difference between the upper sum and the lower sum is 1. The upper sum and the lower sum would not converge to a common value. There are ways to handle functions like this. You have to go beyond analysis, it's measure theory. But there are ways to handle functions that are this wildly discontinuous. So this is why we have to be a little bit careful. All right. Any thoughts as to what we might use to analyze f of uk minus f of lk? Yes. Good. Right. I didn't specifically say what theorem, but good choice. Right. So by the mean value theorem, there's some point ck such that this sum is equal to f prime of ck times uk minus lk. Now it's possible that maybe lk comes after uk, so maybe that's negative. And if this is negative, then this would be negative here as well. So now I'm going to use absolute values. I'll get absolute value of un minus ln is thus equal to 1 over n. The sum k goes from 0 to n minus 1. Absolute value of f prime of ck. And then how far apart can uk and lk be?
1.
I'm sorry?
No.
It's at most 1, but you can do better than 1. How far apart could uk and lk be?
Could be the same.
I'm sorry?
They'd be the
Well, that's the closest they could be. What's the farthest apart uk and lk could be? I agree they could be, they're no more than 1 unit apart. But we actually know they're much closer than 1 unit apart. 1 over n. They live in the interval xk to xk plus 1. Right? So since they live in here, the distance between uk and lk is at most 1 over n. So now that we know that, when we come back over here, this is going to be less equal to 1 over n squared. The sum k goes from 0 to n minus 1 of my big bound b. And since we have n terms in the sum, and each term is at most b, what's the sum? It's at most n times b. And so we get 1 over n squared times nb. This is b over n, and this goes to 0. And that finishes the proof. And all we needed to know was that it was bounded. We didn't need to know what that value was. The value will affect how quickly it goes to 0. But the fact that it's bounded means that this sum will go to 0, so the upper and the lower sums converge. Great, the upper and lower sums converge, so they must converge to the true area. Okay. Any questions on the first part of the proof? So we are almost there. Now we have to do the other part of the proof. We want to find a way to calculate the area and show that the area is essentially just the antiderivative at b minus the antiderivative at a. All right. So here's something really nice we can do. LK times 1 over n is less equal to f of yk times 1 over n is less equal to f of uk times 1 over n for any yk in the interval xk plus 1. And the reason is no matter what point you take, the value of f of yk can't be smaller than f of lk. Lk is where my function is smallest on the interval. And it can't be larger than f of uk. That's where my function is largest. So this has to live between these. So if we sum over k goes from 0 to n minus 1 of f of lk, 1 over n is less equal to the sum, k goes from 0 to n minus 1 of f of yk times 1 over n is less equal to the sum, k goes from 0 to n minus 1 f of uk times 1 over n. So no matter what points you choose, it will always be sandwiched in between. So we have freedom. We want to choose a good sequence of points. And we want to evaluate our function at that sequence of points. What theorem should we use? Mean value theorem, right? This is the lecture on the mean value theorem. When in doubt, mean value theorem. Well, when you use the mean value theorem, you have to apply it to a certain function. You apply it to a function, and then the average speed is the instantaneous speed. If I want to have an f of yk, what function am I applying the mean value theorem to? Which function? There's only 3 functions really under consideration. Yes?
F?
Which f? Be more specific.
Lowercase f.
Well, if I'm doing lowercase, I've only got f at yk here. I'm not subtracting anything else. Can't be little f. So how would you correct it? I want to have something where I'll have f of yk. What function should this be? Or if you want, let me write f of yk in a more illuminating manner. Let me write it as big F prime. So hopefully this highlights that you want to apply the mean value theorem to big F. When you do the mean value theorem, you say g of b minus g of a over b minus a is g prime. Here's my big F prime. So apply mean value theorem to big F. And let yk be the points. Now you'll get big F of xk plus 1 minus big F of xk is big F prime of yk times xk plus 1 minus xk. Well, what's xk plus 1 minus xk? Yes, it's 1 over n. So we get f of xk plus 1 minus f of xk, and then we'll just sum this. K goes from 0 to n minus 1 is going to be a sum. K goes from 0 to n minus 1 of big F prime of yk times 1 over n. And if you want, that's just little f at yk. All right, so we just have to evaluate this sum over here. When you look at what's going on over here, this is sandwiched between the upper and the lower sums. So as n goes to infinity, what does this have to converge to? If it lives between the upper and the lower sums, and the upper and lower sums are converging to a common value, what's that common value that it's converging to? It's the area. So this quantity over here has to be converging to the area as n goes to infinity. It lives between the lower sum and the upper sum. All right. I want you to calculate the following sum. I'm curious to see who can get this fastest. 5 minus 1 plus 7 minus 5 plus 99 minus 7 plus 104 minus 99 plus 1701 minus 104 plus 24601 minus 1701. What does this equal? 24600. How'd you get that so fast?
Because they all cancel,
So they all cancel diagonally. This is called a telescoping sum. All that matters is first minus last. We have a telescoping sum over here. So let me write carefully what we're looking at over here. We have f of x1 minus f of x0 plus f of x2 minus f of x1 plus dot 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 plus f of xn minus f of xn minus 1. So all these things cancel, and we're left with f of xn minus f of x0, or just f of 1 minus f of 0. So what's amazing is this is just f of 1 minus f of 0. So f of 1 minus f of 0 lies between the upper and the lower sums. So for every n, f of 1 minus f of 0 is between the lower and the upper. As n goes to infinity, the lower and the upper converge to a common value. And so that common value must be f of 1 minus f of 0. And this must be the area. So this finishes the proof of the fundamental theorem of calculus. We use the mean value theorem twice. The hardest part is to recognize how do you want to use it. When we had the little f evaluated at yk, we need to notice that that's where we're using the mean value theorem. We want to write this as big F prime. Okay. Any questions about the proof of the fundamental theorem of calculus? So this is the proof. This is one of the biggest results in all of mathematics. We've got a few minutes left, so what I want to quickly do is show you another way to prove the mean value theorem, and it illustrates a really good concept. It's reducing a hard problem to a simpler one. So this is called Rolle's theorem. And what Rolle's theorem says is if you have a continuous function which is differentiable that's 0 at a and 0 at b, then there must be some point in between where the first derivative is 0. So this is just a special case of the mean value theorem. I want to very quickly show how you can deduce the mean value theorem from this special case. Right? So in general, here's a, here's b. Say I have something like this. Right? Let's look at the function g of x is f of x minus f of a. What's the value of this function at a? Just 0. So this is beginning to look like Rolle's theorem. This function g is related to f, and it's 0 when x equals a. Great. Unfortunately, it's not 0 when x equals b. It's f of b minus f of a. All right, so what I'm going to do is I'm going to subtract off f of b minus f of a. And I'm going to multiply that by x minus a over b minus a. When x is equal to a, this term vanishes. And when x equals b, this is now 1. So I've made a small change. If you now look, you get g of a equals g of b equals 0. We can now apply Rolle's theorem to g. G prime of x is just f prime of x. This is a constant. This is a constant. This is a constant. What's the derivative of x minus a? 1. So we get g prime of x is f prime of x minus f of b minus f of a over b minus a. So by Rolle, there exists a c such that g prime of c equals 0. That will give you f prime of c equals f of b minus f of a over b minus a. And that's a proof of the mean value theorem if you know Rolle. Another way of viewing what's going on is I'm just changing my coordinate axes. I'm just leaning back. And if I lean back like this, this is now the situation of Rolle's theorem, where my function is 0 at these 2 points. So this is a really nice concept of reducing a general case to a specific case. If we can do the special case when f of b equals f of a, we can then handle anything. So we've got about 1 minute left. Let me quickly prove Rolle's theorem. So here's A, here's B. If my first derivative is 0 at a, can I find a place where my first derivative is 0? Yes. Similarly, if my derivative is 0 at b, I'm done. So I might as well assume that my derivatives are not 0 at a and b. With all else generality, I can assume my derivative is positive at a. Imagine my derivative was negative at b. Well, this means my function is increasing to come to here, and it's decreasing to get down to b. So there must be a place in between where the derivative was 0. This is just the intermediate value theorem. If instead the first derivative was positive here, then I'm increasing upward like this. My function was initially positive over here, it was negative down here. There must be some place where my function comes down into the negatives. So my function must be decreasing. So there must be some intermediate point where my first derivative was negative, and then I can apply the intermediate value theorem again. So this was a little bit fast at the end. I'm just trying to give you a sense of how you can attack these problems, how you can try to make them more theoretical. This is not an advanced post-core 300 level math class. But I want to show you a little bit of what's out there, so if you decide that this is something you want to pursue, you have a good sense. All right.